So now let's begin the proof of the Tietze extension theorem. So the idea is to, given a function f from some closed subspace A to AB, we construct a sequence of functions Sn converging. So Sn is a sequence of continuous functions. So sequence of continuous functions Sn. So each Sn is now defined on the whole space X and taking values in AB. And we will construct it in such a way that the sequence Sn such that Sn converges uniformly. So the sequence converges uniformly, therefore the limit of this sequence is going to be continuous. And for each A in A, we have Sna is converging to f of A. And therefore, when you take the limit of these functions Sn and restrict it to the subset A, then it coincides with f. So this is what we want to show. So it has again a kind of a recursive definition of a proof, and we will take it step by step. So in the first step, we suppose that a continuous function h from A to a particular type of interval, which is of the form minus r is given. Okay, so once this continuous function is given, we want to create a function g defined. So we construct a continuous function g from X to the set minus r such that we have, first of all, that the modulus of gx is less than or equal to r by 3, and the difference of ha minus ga is less than or equal to 2r by 3. So for all a, so this is for all x and this is for all a in A. And we are going to take this construction. So then step 1 is just this particular construction, and then from step 2 onwards we will use a recursive definition. So let's see how to construct this continuous function such that it satisfies these two properties. In fact, here we can even ensure that the function g is has the image in the subset minus r by 3 to r by 3 rather than minus r to r. So let us see how this works. So to do this, so we have this interval minus r to r, and we have 0 here. So we are going to break it up into 3 parts. So the first part is minus r to minus r by 3. The second part is minus r by 3 to r by 3, and the third part is r by 3 to r. So this is, let's call this I1, let's call this I2, and let's call this I3. So we are going to divide our image domain, rather. So we have divided our image subset minus r to r in 3 parts. So we have I1 is equal to minus r to minus r by 3, I2 is minus r by 3 to r by 3, and I3 is r by 3 to r. Now let B be the inverse image of f, h inverse of I1, and C be h inverse of I2. So since h is a continuous function is continuous, then so B and C are closed disjoint subsets in A, so in the subspace topology of A, but since A is closed itself, but since A is closed, so B and C are closed disjoint sets in X also. And so now we have a pair of closed disjoint sets, then we can use the Urysohn's lemma, right? So by Urysohn's lemma, so what do we have? So we have a function, there exists a continuous function g from x to minus r by 3 to r by 3, such that g g restricted to b is equal to minus r by 3 and g restricted to c is equal to plus r by 3. So so we get this continuous function, and this function g will automatically satisfy the properties that we want. So we claim that first of all that gx, the absolute value of gx, is less than r by 3 for all x, and secondly ha minus ga is less than or equal to 2r by 3 for all a in x. So let's see why these two properties hold. So the first property here, so one is trivially true since g was constructed to be a function that lands in the subinterval minus r by 3 to r by 3. So therefore the modulus of gx is less than or equal to r by 3. So the first one is okay. So to show the second one, so we have three cases. So if a belongs to b, which is h inverse of I1, then both HA and GA belong to I1. So HA belongs to I1 because A belongs to H inverse I1, and GA belongs to I1 because G restricted to B. So sorry, here it should be X rather than A rather than X. So here so take A in A, and now we have these three cases. So if A is in B, which is H inverse I1, then both HA and GA belong to I1, and so this is true because GA is equal to minus r by 3. Okay, so the difference of these values HA minus GA is less than or equal to the diameter of I1, which is nothing but 2r by 3. And similarly if A belongs to C, which is H inverse I2, then both HA and GA belong to I3, and then we have HA minus GA is again less than or equal to 2r by 3. So just a slight correction here, I have taken C to be H inverse I2, but it should be H inverse I3, and that's how we get I1 and B and C to be disjoint closed sets. Okay, so that said, we come back to our claims. So if A belongs to either B or C, then we see that this is okay. However, if A does not belong to B union C, then HA belongs to I2, and so does GA. So GA is already in I2. So this is nothing but minus r by 3 to r by 3, and therefore this implies that the distance between GA and HA is again less than the diameter of I2, which is again 2 by 3. So we see that HA minus GA, the modulus of it is bounded above by 2r by 3 for all A in A. And we are going to now use this it's like a lemma, small lemma, and we are going to repeatedly use it. So let's see the next steps which we will in which we will use kind of recursive definition. So let's begin the next step, and here we make a simplifying assumption. Without loss of generality, we replace the interval AB by -1, 1. So we are given a function. So given f is a continuous function from A to -1, 1. And now we have to find an extension of this continuous function f. So here take r equal to 1 and h to be this function f, and repeat and apply the result that we got from step 1. So this means that there exists a continuous function which we shall call g1 from x to -1 by 3 to 1 by 3, such that we have modulus of g1x is less than or equal to 1 by 3 for all x in x, and secondly modulus of f a minus g1a is less than or equal to 2 by 3 for all A in A. So we are just replacing r by 1 and h by f. That's all we are doing, and then we are taking the constructed function g in step 1, and we are calling it g1. This is because we are going to use a recursive definition. And similarly in step 3, let r be equal to 1 by 3 and h be equal to f minus g1. So f minus g1, so then h is a continuous function from A to the set -1 by 3 to 1 by 3. Okay, so this is minus r to r. So why is f minus g1 landing here? Well, this is simply because since modulus of f a minus g1a is less than or equal to 2 by 3, and g1a belongs to -1 by 3 to 1 by 3. And now in the next step, in step 3, we let h to be equal to f minus g1 and r to be equal to 2 by 3. So then h is a function, continuous function from A to minus r. This is simply because of the properties of f and g1. So since g1 of A belongs to minus r by 3 to rather 1 by 3 to 1 by 3, and modulus of f a minus g1a is less than or equal to 2 by 3. So this means that modulus of h of a is less than or equal to 2 by 3, and this is exactly what is given here. So this is the same as saying that h with the domain A lands in the interval minus 2 by 3 to 2 by 3. Okay. So So we have this function now h, and then again using again step 1, we get a continuous function g2 from x to minus r by 3 to r by 3, such that we have modulus of g2 x is less than or equal to 1 by 3 times r, which is 1 by 3 times 2 by 3, and the modulus of h a minus g2a is less than or equal to 2 by 3 times r, which is equal to 2 by 3 whole squared. And this is by the way nothing but fa minus g1a plus g2a. Okay, and so this is nothing but this is less than or equal to 2 by 3 whole squared. And we are seeing that we are getting a sum of functions, and we are going to repeat this construction and again, and we are going to get a sequence of functions which will sum up in a series, and this because of this kinds of results, it will converge uniformly by the Weiestrass M-test. So let's continue. So in the step 4, so this is a general step, general induction step, and in this step we have constructed, so given functions g1, g2 up to say gn, such that we have modulus of g and x is less than or equal to 1 by 3 times 2 by 3 to the power n, and secondly we have fa minus the sum of k equal to 1 to n gkx, this is less than or equal to 2 by 3 to the power n. So in the by n steps we have constructed this, and again using step 1, we construct gn plus 1, which is again the continuous function from x to minus r by 3 to r by 3, with r equal to 2 by 3 to the power n, and h equal to f minus this sum k equal to 1 to n gk. So so using step 1, we construct this function gn plus 1, and which satisfies again a similar, it satisfies the modulus of gn plus 1 x is less than or equal to 1 by 3 times 2 by 3 to the power n, and secondly that f of a minus the sum from k equal to 1 to n plus 1 now gkx modulus is less than or equal to 2 by 3 to the power n plus 1, and in fact here one should have n minus 1. So so in this way we construct a sequence of functions gk which has these two nice properties. Now we let gk to be the sum of all these functions. It's a series of functions gkx. So with the Weiestrass M-test, we have that this series converges uniformly, and this is because of the first property that gkx is bounded above by 1 by 3 times 2 by 3 to the power k minus 1, and this the sum of these things converges. So this is by the Weiestrass M-test, then the series converges uniformly, and in fact this series equals 1. So in fact the modulus of gx is less than or equal to 1, which implies that g is a function from x to minus 1 1, which we wanted. And secondly, g is continuous by the uniform limit theorem. This is automatic. And the third part is the most important part. When you have the partial sums, then f of a minus Sna by construction is bounded above by 2 by 3 to the power n, and therefore Sna converges to Fa for all a in A, and this was our goal, and therefore we have proved the Tietze extension theorem.